long before the first stars blazed to life, the universe was a realm of pure darkness, a vast, unknown expanse where the fundamental rules of existence were still being written. In this cosmic void, could there have been stars unlike any we know? Immense, strange giants known as dark stars, glowing not with nuclear fusion, but with the elusive energy of dark matter. Dark matter, the invisible force holding the cosmos together, might have fueled these stars through the annihilation of its particles, a process we are only beginning to understand. These hypothetical dark stars challenge our comprehension of the early universe, suggesting a hidden physics at play. Recently, the James Webb Space Telescope has brought us closer to unraveling this mystery by identifying 3 potential dark star candidates. These objects, initially mistaken for early galaxies, may each be 1,000,000 times more massive than our Sun, powered by dark matter. If confirmed, they could revolutionize our understanding of the universe's infancy and provide crucial insights into the nature of dark matter, one of science's greatest enigmas. Join us as we delve into the universe's earliest moments to explore the enigma of dark stars and chase the light that started it all. Before light first pierced the void, before the universe shimmered with the stars we now chart across our skies, there was something else, something quieter, older, and wrapped in shadows. This was a time before the cosmos spoke in the language of light, before its galaxies performed their luminous dance, before time as we know it had direction. It was the unseen beginning, and though it left no direct trail of photons to follow, it carved the stage for everything that followed. It is here, in this most ancient epoch, that the answers to our deepest cosmological questions may lie. When we look up at the stars, we're seeing ancient light, light that has traveled millions or even billions of years to reach our eyes. The James Webb Space Telescope has pushed this boundary further than ever, seeing nearly back to the formation of the first galaxies. But what lies beyond even that? What existed in the darkness before the light? These questions are more than academic. They challenge the very core of physics and our understanding of what reality is and where it began. The prevailing narrative of cosmic origin begins with the Big Bang, a singularity where space, time, matter, and energy all burst into existence. But this wasn't a bang in the way we usually imagine. It was a rapid expansion from an incomprehensibly small point, a smooth unfolding of energy and space. For the first 380,000 years, the universe was opaque, a hot, dense plasma of photons, electrons, and protons, all crashing into one another. Light couldn't travel freely. It was constantly scattered in this charged fog. Eventually, this soup cooled enough for electrons to combine with protons and form neutral hydrogen atoms, a moment called recombination. With the electrons locked into atoms, photons could finally move unhindered through space. This released what we now see as the cosmic microwave background, CMB, the oldest light we can detect directly. It's a snapshot of the universe at about 380,000 years old. But what happened before that? What existed in the first second, the first minute, the first 1,000 years? Most telescopes, including Hubble, couldn't answer that. They couldn't see through the fog. But now, cutting-edge physics, subtle data in the CMB, and ambitious missions like JWST are hinting at something strange lurking in that void. The time before light, a hidden era, a time of dark stars and forbidden physics. To understand this ancient darkness, we must first accept a simple but troubling idea. Our current understanding of physics might not apply. The early universe didn't follow the tidy rules we've spent centuries defining. Gravity, as we know it, might have been warped. Quantum fluctuations could have stretched across space-time like spiderwebs. Matter may not have existed in recognizable forms. Even time itself might have ticked differently. This is where forbidden physics enters the scene. Not forbidden as in illegal, but forbidden in that they defy the conventional framework of reality. In this pre-light cosmos, normal matter had yet to form. There were no atoms, no molecules, no planets or stars. Instead, theorists believe dark matter and dark energy may have dominated the scene. These mysterious components, which still account for 95% of the universe's content today, were possibly even more powerful in those early seconds. Could they have given rise to objects we've never observed? Some scientists now speculate that before stars formed from ordinary matter, exotic dark stars, hypothetical objects powered not by fusion, but by the annihilation of dark matter, may have burned in the darkness. These are not just science fiction ideas. They are gaining traction in serious cosmological models. A dark star wouldn't shine with light, but with something else. Perhaps subtle emissions of neutrinos, gravitational waves, or strange particles that don't interact with light at all. They could be massive, much larger than modern stars, yet almost completely invisible to our best instruments. If they existed, they would be the universe's first structures, emerging from the chaos of the Big Bang and setting the stage for everything to follow. To trace these origins, physicists must dive into some of the most complex and counterintuitive theories ever devised. String theory, loop quantum gravity, and inflation theory all attempt to model the rules that may have governed the first moments. These aren't just mathematical games. They're attempts to replace our known physics with something that could explain the birth of space-time itself. What is space when it's smaller than an atom? What is time when each tick of the clock is stretched across dimensions we cannot perceive? One promising idea is cosmic inflation, which posits that the universe expanded faster than the speed of light for a tiny fraction of a second, immediately after the Big Bang. This expansion smoothed out the wrinkles in spacetime and created the uniformity we see in the CMB. But inflation might have also stretched quantum fluctuations into the seeds of galaxies. These fluctuations, tiny blips in the quantum vacuum, could have rippled out and shaped the very structure of the cosmos. And then there's the possibility of multiple universes. Some physicists suggest that inflation didn't just happen once, but continuously in different regions, spawning countless bubble universes, each with its own laws of physics. If that's true, then our universe might be just one small room in an endless mansion. In the early, pre-light darkness, these multiversal bubbles could have collided, merged, or influenced one another in ways that subtly sculpted our own cosmic landscape. But why does this matter now? Why go back to a time before light? Because every atom in your body, every star in the sky, and every galaxy that paints the heavens was forged from the conditions set in that hidden age. To truly understand who we are, we must explore not just the light, but the darkness that came before it. As the James Webb Space Telescope begins its historic mission, it's already peering back further than ever before. But its true potential lies not just in seeing the first galaxies, it's in detecting the shadows of what came before. Slight variations in the light of ancient galaxies, subtle signals in the hydrogen clouds, or strange gravitational fingerprints may be our only clues to the unseen beginning. It's like trying to reconstruct the first pages of a burned book by examining the ashes. And yet, piece by piece, scientists are doing just that. In the coming years, we may finally gather enough evidence to confirm or deny the existence of dark stars, test the limits of forbidden physics, and peer into the moments when the universe was still writing the rules of reality. This journey doesn't just reshape our understanding of space and time. It redefines the very essence of existence. Before the light came, before the stars were born, there was something ancient, powerful, and hidden. And now, at last, we are daring to look it in the eye. The cosmic landscape after the Big Bang, often referred to as the Age of Darkness, is a period in the universe's history that remains shrouded in mystery, a time when light had not yet pierced the vast expanse of space. It was a time of profound transformation, one that paved the way for the stars and galaxies that would later illuminate the universe. This era, beginning immediately after the Big Bang and extending for millions of years, is not the familiar, vibrant cosmos we observe today, but a dark, formless void of matter in its most primal state. Understanding this era requires us to journey deep into the heart of the universe's infancy, exploring a realm dominated by plasma, hydrogen, and the strange, often incomprehensible laws of physics that governed its existence. In the aftermath of the Big Bang, the universe was in an extremely hot and dense state, characterized by rapid expansion. For the first few 100,000 years, the universe was a turbulent place. Temperatures soared to unimaginable heights, and the matter was in a plasma state, a hot soup of particles like protons, neutrons, and electrons. This plasma state was not conducive to the formation of atoms or the transmission of light as we understand it today. The radiation from the Big Bang, the cosmic microwave background, CMB, was scattered by free electrons in this plasma, preventing light from traveling freely through space. In this sense, the universe was a glowing, chaotic mess of energy and particles, a time when the universe was opaque to the light that we now rely on to understand cosmic history. At the core of this early universe were hydrogen atoms. In fact, hydrogen made up most of the visible matter during the Age of Darkness. However, these hydrogen atoms and their counterpart, helium, were not in their usual, stable forms. They existed as charged particles, ions, floating in a sea of high-energy radiation. This primordial state of matter, often referred to as the photon-baryon fluid, was highly energetic and could not form stable structures. The universe at this point was essentially a featureless plasma soup, with little structure beyond random fluctuations in temperature and density. During this period, gravity, the fundamental force that would later govern the formation of stars and galaxies, had a key role to play. However, without the cooling necessary for atoms to form, gravity had no easily accessible material to coalesce into larger structures. This is why, despite the universe's immense size and the presence of a vast amount of matter, stars and galaxies had not yet formed. The early universe's density was still too high and temperatures too extreme to allow any clumping of matter into recognizable cosmic objects. As the universe expanded and cooled, a crucial process began to unfold. It was during this time, known as recombination, that the temperature dropped enough for electrons and protons to combine and form neutral hydrogen atoms. This allowed light to travel freely through space for the first time, creating the cosmic microwave background radiation, the faint afterglow of the Big Bang. This transition from a plasma-filled universe to one in which light could travel freely was a significant milestone, but it didn't immediately lead to the formation of stars. For millions of years after this shift, the universe remained dark, with no light sources to illuminate the vast expanses of space. This time is often referred to as the Dark Ages of the universe, because, though the universe had cooled sufficiently for light to travel, No stars or galaxies had yet formed to provide the visible light we now associate with the cosmos. It was a time dominated by neutral hydrogen gas and dark matter, the invisible substance that was theorized to exist but remained undetectable through direct observation. In these dark times, gravitational forces slowly began to take over, with hydrogen gas gradually clumping together, forming the first seeds of galaxies and stars. The Age of Darkness is also a time when the laws of physics were in a state of fluidity, especially when we look at the strange, unseen forces that were beginning to shape the universe. For example, dark energy, still one of the biggest mysteries in modern physics, began its subtle influence on the expansion of the universe during this era. The presence of dark energy, which scientists believe is responsible for the accelerating expansion of the universe, was likely one of the driving forces behind the universe's transition from the dense, hot phase of the Big Bang to the cooler, more spacious era that followed. The Age of Darkness is therefore a critical point in cosmic history, not just because of its darkness, but because of the forces, both seen and unseen, that began to shape the universe we know today. In addition, the fundamental laws of physics were still evolving during this time, especially in terms of how gravity interacted with the universe's newly forming matter. These early interactions laid the groundwork for the gravitational collapse that would eventually lead to the formation of the first stars, objects that, despite their size and brightness, would still be millions of years away from emerging. In sum, the Age of Darkness represents a fascinating and pivotal chapter in the history of the universe. It was a time of transition, where the laws of physics, still untested in such extreme conditions, would gradually give rise to the stars, galaxies, and cosmic structures we recognize today. The plasma and hydrogen that dominated this period were not the end of the story, but rather the beginning of a long and intricate evolution of matter and energy. As we probe deeper into the mysteries of the early universe, we continue to uncover more about this enigmatic era, an age not only of darkness, but of potential, waiting to be ignited by the forces of nature that would eventually give birth to the cosmos as we know it. The birth of dark stars marks a momentous chapter in the early history of the universe, an era when the cosmos was an unexplored and enigmatic frontier. As we peer deeper into the universe's infancy, we begin to unravel the possibility of stars unlike anything we recognize today. These stars, known as dark stars, represent a fusion of exotic physics and dark matter, an entirely hypothetical class of celestial giants that could have shaped the cosmos in ways that remain largely beyond our comprehension. Dark stars are far from the familiar objects of stellar birth that we are accustomed to, such as the Sun. Instead of being fueled by the nuclear fusion of hydrogen and helium at their cores, these behemoths would have drawn their energy from an entirely different source: dark matter, annihilation. But what does that mean, and how does it reshape our understanding of the universe's early moments? In the conventional view of star formation, gravity pulls gas and dust together, leading to nuclear fusion in the star's core, releasing immense amounts of energy in the form of light and heat. Dark stars, however, would have been governed by a fundamentally different set of principles. These hypothetical objects would have formed in the cosmic dark ages, the period immediately following the Big Bang, when the universe was filled with gas clouds, predominantly made up of hydrogen and helium. While the universe was still shrouded in darkness, a key ingredient for the formation of dark stars already existed: dark matter. Dark matter, the mysterious, invisible substance that makes up a significant portion of the universe's mass, was already present in the early universe. While it doesn't interact with electromagnetic radiation, light, and therefore remains undetectable by conventional means, it interacts gravitationally with ordinary matter. In fact, dark matter was crucial in influencing the formation of the first structures in the universe, including galaxies. It also played a pivotal role in the birth of dark stars. The theoretical process behind the formation of dark stars is both fascinating and mysterious. According to leading models, dark matter particles in the early universe could have slowly accumulated at the centers of gas clouds. These particles, which are expected to be much more massive than ordinary matter particles, might have eventually started interacting with one another. When two dark matter particles collide, they could annihilate each other, releasing energy in the form of heat. This energy, while not the same as the energy produced by nuclear fusion, would have been enough to provide the outward pressure necessary to support the star against the crushing force of gravity. Thus, rather than relying on fusion reactions like conventional stars, dark stars would have been powered by the annihilation of dark matter, an energy source far more exotic and mysterious. Dark stars would likely have been enormous, many times more massive than our Sun, and could have been as much as 1,000,000 times larger in diameter. Their sheer size would have been necessary to balance the immense gravity pulling inward with the heat generated by dark matter annihilation. Despite their size, these dark stars would not have emitted light in the visible spectrum like normal stars. Instead, their glow would have been in the form of infrared radiation, a faint heat signature that would have been incredibly difficult to detect. To the naked eye, they would have remained in the shadows of the universe, their presence only hinted at by the complex gravitational interactions they would have exerted on the surrounding matter. The role of dark stars in shaping the early universe is not merely hypothetical. They could have been the precursors to the first true stars. In the absence of a stable, light-producing fusion process, dark stars would have created a critical environment for further cosmic evolution. Their immense size and gravitational influence could have played a crucial role in initiating the collapse of gas clouds, leading to the eventual formation of the first population. 3 stars, the first stars to undergo traditional hydrogen fusion. These initial fusion-powered stars would have been responsible for creating the first heavy elements, paving the way for the formation of galaxies, planets, and ultimately life itself. However, the story of dark stars does not end with their creation. These stars, due to their size and the peculiar nature of their energy source, wouldn't have lived as long as ordinary stars. Dark stars would have eventually burned through their dark matter supply, causing them to collapse inward, triggering a violent supernova-like event. This process would have resulted in the formation of black holes, which in turn could have become the centers of early galaxies. Thus, the birth and death of dark stars could have set the stage for the formation of some of the most fundamental structures in the universe. The idea of dark stars pushes the boundaries of our understanding of astrophysics, challenging our traditional models of star formation and energy generation. Their theoretical existence opens up new avenues of exploration into the role of dark matter in cosmic history. These elusive giants may have played a far more significant role in shaping the universe than we realize, and their study could offer unprecedented insights into the fundamental forces that govern not only the stars, but also the dark, unseen universe that surrounds them. In sum, the birth of dark stars is an exciting concept that brings together the mysteries of dark matter, gravity, and the very nature of energy in the early universe. Although their existence has yet to be confirmed through direct observation, dark stars are an integral part of the puzzle that astrophysicists are still trying to solve. They remain one of the many elusive and fascinating pieces of the universe's origin story, a story that continues to unfold before our eyes, offering new revelations with each discovery. The birth of dark stars marks not just a chapter in the early universe, but a tantalizing clue to the forces that shaped the cosmos as we know it today. The universe before the birth of light is a mystery that continues to puzzle scientists, one that challenges the very core of what we understand about the cosmos. This period, referred to as the Cosmic Dark Ages, existed in the wake of the Big Bang, but before the first stars ignited, leaving the universe in an era of absolute darkness. In this enigmatic state, the universe was vastly different from what we observe today. No stars lit up the skies, no galaxies formed as they are now, and no visible light or radiation pervaded the space. Yet, in this darkness, the universe was far from empty. Instead, it was alive with unseen forces, particles, and energies that we are only beginning to unravel through modern scientific tools. This era predates the formation of stars and galaxies, existing in a time when hydrogen, the simplest element, was the dominant component of the universe, existing in a hot and dense plasma state. The fabric of the universe was full of potential, waiting for the right conditions to give birth to the stars that would eventually light up the cosmos. But the true nature of what happened in this pre-light period is shrouded in mystery. We are left with fundamental questions. What defined the universe before stars, light, and the structures we see today? What forces were at play during this time, and how did these forces shape the cosmos that emerged from this era? As we delve into the heart of this mystery, we encounter the speculative and fascinating idea of dark stars. These hypothetical giants are theorized to have existed in the earliest phases of the universe, possibly even before stars as we know them. Rather than being powered by nuclear fusion, as the stars we observe today are, dark stars would have been driven by the annihilation of dark matter, an invisible, elusive substance that makes up a significant portion of the universe's mass, but cannot be directly observed. Instead of emitting light through fusion reactions, these early stars would have radiated energy through interactions with dark matter, providing a completely different source of power that defies the conventional understanding of star formation. Dark stars are not just interesting because they challenge our ideas about star formation. They also present a key to understanding the physics of the early universe. In the absence of normal matter and light, gravity and quantum forces were likely behaving in ways that defy our modern understanding of physics. In the strange, fluid environment of the early universe, quantum fluctuations, tiny, unpredictable variations in energy at the smallest scales, could have had massive implications for the universe's formation. These fluctuations in energy and matter likely influenced the structure of the cosmos at its very inception, setting the stage for the formation of galaxies and larger cosmic structures. The conditions at this time were so extreme that gravity, the force that governs the motion of all matter, could have acted very differently than it does today. The extreme density and energy of the universe might have caused gravity to behave in ways that don't align with the laws we currently understand, challenging the foundations of modern physics. The era of darkness also saw the influence of dark matter, a mysterious and invisible form of matter that has yet to be directly detected. Although we cannot see dark matter, its presence is inferred through its gravitational effects on visible matter, and it is believed to make up most of the mass in the universe. In the early universe, dark matter would have had a much more significant role to play. The dark matter interactions could have been far stronger than what we observe in the present day, possibly contributing to the birth of dark stars. These interactions with dark matter might have altered the behavior of gravity and other fundamental forces, creating conditions that are beyond the scope of conventional physics. As we consider the early universe and its strange, alien laws of physics, we are forced to confront the idea that the universe's birth was not a simple process. The speculative physics that governs the Dark Ages challenges the foundations of everything we thought we knew about the cosmos. In this age of mystery, the laws of physics may have been dramatically different, shaped by quantum fluctuations, altered gravity, and the influence of dark matter, creating a universe in which the normal rules of nature no longer applied. These unconventional laws of physics, often described as forbidden physics, open up a world of possibilities that extend beyond our current understanding. What if gravity, for instance, behaved differently at certain scales, influencing the behavior of dark matter and other cosmic structures? What if quantum fluctuations could give rise to entire universes or regions of space-time that defy conventional understanding? The existence of dark stars powered by dark matter annihilation may be one of the clearest examples of how the early universe defied the laws of physics as we know them. These dark stars, though still theoretical, could offer insights into how the cosmos was shaped by forces beyond our current comprehension. The universe before the arrival of light and the formation of stars remains a profound mystery, one that science is only beginning to explore. In this early age, speculative physics and strange laws of nature governed the birth of the cosmos, challenging our understanding of gravity, quantum mechanics, and dark matter. The possibility of dark stars, fueled by dark matter annihilation rather than nuclear fusion, presents an exciting and unexplored avenue of research that could unlock answers to the questions about the universe's beginning. As we continue to push the boundaries of our knowledge, we may one day uncover the full extent of the forbidden physics that govern the birth of the cosmos, revealing secrets that are currently beyond our reach. As humanity delves deeper into the mysteries of the cosmos, we are confronted with the profound realization that our understanding of the universe's beginnings is still in its infancy. The cosmic dawn, an era that followed the Big Bang, is the pivotal stage in the universe's evolution where light and matter began to take their first, fragile steps towards the creation of the complex, structured cosmos we observe today. This is a time long before the birth of stars, galaxies, and even the first specks of light. Yet it is during this shadowed epoch that some of the most critical foundations of the universe's future were laid. In this void of cosmic history, a fascinating concept arises: the notion of dark stars. These enigmatic objects, though hypothetical, offer a tantalizing glimpse into a cosmos that operates by rules and forces far beyond our current comprehension. Rather than relying on the fusion processes we see in modern stars, dark stars are theorized to be powered by the annihilation of dark matter. Dark matter, the invisible substance that accounts for a significant portion of the universe's mass but remains undetectable by conventional means, could have been the driving force behind the formation of these giant stellar objects in the early universe. Instead of the nuclear reactions that occur within the cores of today's stars, dark stars would have drawn energy from the interactions between dark matter particles, their gravity and mass likely growing to immense proportions in the process. At first glance, dark stars seem like the stuff of science fiction, but they play a pivotal role in the story of the universe's early days. The concept of these objects arises from a need to explain the rapid formation of the first galaxies and large-scale structures in the universe. After the Big Bang, the universe was a dense, chaotic soup of particles, dominated by plasma and hydrogen gas. Yet in this seemingly barren expanse, the seeds for the universe's grand structures were planted, structures that would evolve into the galaxies, stars, and black holes that populate the cosmos today. Dark stars are theorized to have played a central role in this process. Dark stars were not just massive celestial bodies in their own right, but also served as the catalysts for the formation of larger-scale cosmic structures. Their immense mass would have generated enormous gravitational forces, pulling in surrounding hydrogen and helium gas to create the very first proto-galaxies. These dark stars would have acted as the architects of the early universe, shaping the distribution of matter and influencing the formation of galaxies as we know them. As these stars grew and matured, they could have triggered the formation of black holes, marking the beginning of a new era of cosmic evolution. In fact, some theories suggest that dark stars may have been the precursors to the supermassive black holes we observe at the centers of galaxies today. But for all the awe-inspiring possibilities that dark stars represent, they remain purely hypothetical. Despite our best observational tools and the development of increasingly sophisticated models of cosmic evolution, we have yet to uncover definitive evidence for the existence of these dark behemoths. The gap between theoretical predictions and observational data is vast, and while some argue that the cosmic microwave background, CMB, radiation may hold faint traces of dark stars, others maintain that we are still a long way from truly confirming their existence. The gravitational waves that ripple through space-time, another tool in the astronomer's arsenal, may one day reveal the faint echoes of dark stars, but again, we have yet to detect their definitive signature. The absence of evidence for dark stars raises another set of profound questions. Why would such a significant component of the early universe have disappeared so suddenly? How could such massive structures have faded from existence without leaving behind more detectable traces? If dark stars were indeed responsible for the formation of the first galaxies and black holes, where are they now? Did they collapse into the black holes we observe today, or were they destroyed by other, yet unknown cosmic events? The sudden disappearance of dark stars remains one of the most perplexing aspects of the early universe. One possibility is that these stars simply exhausted their dark matter fuel, leading to their collapse into black holes. Another theory is that the dark matter that powered these stars was gradually replaced by more traditional forms of matter, leading to the eventual birth of stars powered by nuclear fusion. In either case, the abrupt end of these enigmatic objects marks the transition from a universe governed by dark matter to one that follows the more familiar laws of physics as we know them today. The mysteries surrounding dark stars also offer a glimpse into the far-reaching implications of the universe's earliest epochs. The cosmic dawn was a time when the very laws of physics may have been in flux, when the universe itself was still evolving, and its fundamental forces were yet to settle into the patterns we observe today. The gravity that governed dark stars, the influence of dark matter, and the very nature of space-time itself may have operated in ways that defy our current understanding. And as the dark stars disappeared, they may have left behind a profound imprint on the universe, an imprint that still echoes in the structures and phenomena we observe today. The connection between dark stars and the formation of black holes is also a crucial aspect of this mystery. In many ways, the fate of dark stars is intertwined with the birth of the first supermassive black holes. These black holes, which reside at the centers of many galaxies, are thought to have formed in the aftermath of the collapse of the earliest stellar objects. Some scientists speculate that the collapse of dark stars may have given birth to these supermassive black holes, which would go on to shape the evolution of galaxies and cosmic structures. Despite the many tantalizing theories about dark stars and their role in the universe's early history, the lack of concrete evidence leaves us with more questions than answers. As we look deeper into the cosmic past, we are confronted with the realization that our understanding of the universe's origins is still far from complete. The evidence we seek may be hidden in the farthest reaches of space, or it may lie in the subtleties of the cosmic microwave background radiation. It may even require new technologies and breakthroughs in physics to uncover the secrets of this distant time. The legacy of dark stars, though, is undeniable. They are a testament to the mysteries that lie in the deepest, darkest corners of the cosmos. As we continue our search for evidence of their existence, we are reminded of the vastness of the unknown, of the countless questions that remain unanswered, and of the infinite possibilities that lie ahead in our quest to understand the origins of the universe. In the shadows of the cosmic dawn, the dark stars remain a profound enigma, a reminder that we are only just beginning to scratch the surface of the universe's most ancient mysteries. And as we continue to explore the farthest reaches of space, we may one day find the key that unlocks the secrets of this lost epoch, revealing the hidden history of the universe and the forces that shaped it in its earliest days. The cosmic dawn may have passed, but the shadow it cast still lingers, waiting to be discovered. As humanity's understanding of the cosmos continues to evolve, the search for answers to some of the most profound questions in astrophysics remains unyielding. The pursuit of dark stars, hypothetical behemoths believed to have dominated the early universe, has become one of the most tantalizing quests in modern cosmology. Though dark stars remain speculative and elusive, their potential to unlock mysteries about the formation of the universe, the nature of dark matter, and the origins of light and energy is too significant to ignore. Among the most promising avenues in the search for evidence of dark stars are the cosmic microwave background, CMB, and gravitational waves. These remnants of the early universe, fundamental to our understanding of cosmology, may contain the faintest echoes of these enigmatic objects that once bathed the young universe in a peculiar glow. The CMB, a faint, pervasive radiation that saturates every inch of space, is a relic of the Big Bang. It represents the afterglow of the universe's formation, providing a snapshot of the cosmos just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space. The CMB is an invaluable tool for understanding the structure and evolution of the early universe, as its temperature fluctuations carry with them vital information about the density of matter, energy, and the forces that shape the cosmos. In a sense, it is a cosmic fingerprint that bears the mark of the universe's birth. These fluctuations, however, may hold more than just the story of the Big Bang. They could also be an imprint of the dark stars that may have existed during the first few 100 million years. At its core, the search for dark stars in the CMB is about identifying tiny anomalies in these temperature fluctuations that would indicate the presence of dark matter, which is hypothesized to power these stars. Dark stars, unlike conventional stars, would have drawn their energy not from nuclear fusion, but from the annihilation of dark matter particles. These dark matter particles are theorized to interact with each other and annihilate, releasing energy in the process. This process could have powered early stars, making dark stars a unique form of cosmic body, distinct from those that rely on fusion. This energy would have impacted the early universe's dynamics, altering the distribution of matter and the temperature of the surrounding gas. As a result, dark stars would leave behind an imprint on the CMB, manifesting as small yet discernible fluctuations in the cosmic temperature and density. But detecting these signatures is no small feat. The CMB is teeming with a multitude of signals, everything from the radiation left by the Big Bang to the faint traces of the first atoms. Distinguishing the potential influence of dark stars from these other sources requires careful analysis and highly advanced observational tools. The Planck satellite, a space telescope launched by the European Space Agency, has provided detailed observations of the CMB, mapping its temperature fluctuations with unprecedented precision. However, even with this advanced data, finding direct evidence of dark stars remains elusive. The imprints left by dark stars would likely be subtle, perhaps blending with the overwhelming noise from other sources, making it incredibly difficult to tease them out from the vast expanse of cosmic data. Yet, scientists are not giving up. Every new dataset provides a potential breakthrough, and even the smallest anomaly could reveal the existence of these strange and exotic objects. While the CMB remains a promising source of evidence, another avenue of investigation lies in gravitational waves. These ripples in space-time, caused by the acceleration of massive objects, were first predicted by Einstein in 1915 as a consequence of his theory of general relativity. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the groundbreaking detection of gravitational waves resulting from the merger of two black holes, marking the first direct observation of these elusive ripples. Since then, gravitational wave astronomy has blossomed into a vibrant field, providing insight into some of the most violent and energetic events in the universe, including the collision of neutron stars and black holes. Gravitational waves, like the CMB, hold immense potential for shedding light on the existence of dark stars. While dark stars would not have been as violent or as compact as black holes or neutron stars, they would have still exerted considerable gravitational influence on their surroundings. The immense mass of dark stars, powered by dark matter annihilation, would have created ripples in space-time, potentially producing gravitational waves detectable by future observatories. Although dark stars are unlikely to have produced the same powerful bursts of gravitational waves associated with black hole mergers, their influence on the surrounding space could have generated faint ripples in space-time, detectable by the next generation of gravitational wave detectors. These gravitational waves, if they exist, would be much more subtle and difficult to detect than those generated by more dramatic cosmic events. However, as gravitational wave detectors like the proposed Laser Interferometer Space Antenna, LISA, and future upgrades to LIGO continue to evolve, the sensitivity of these instruments will improve, providing an opportunity to capture faint gravitational waves from the earliest epochs of the universe. These waves could contain vital information about the existence of dark stars, providing an unprecedented glimpse into the early stages of cosmic history. The quest to find dark stars in both the CMB and gravitational waves highlights a fundamental tension in modern cosmology: the gap between theoretical predictions and observational reality. Dark stars, as a theoretical concept, offer a potential explanation for several unresolved questions about the early universe. For instance, they could explain the apparent discrepancy between the amount of visible matter and dark matter in the cosmos, as well as the rapid formation of the first galaxies. Despite their promise, however, no definitive observational evidence for their existence has been found. The theoretical models predict a distinct imprint of dark stars in both the CMB and gravitational waves, but these signatures have yet to be observed with certainty. This tension between theory and observation adds a layer of intrigue to the search for dark stars. On one hand, the theoretical framework surrounding dark stars is robust, with predictions rooted in our understanding of dark matter, quantum mechanics, and gravity. On the other hand, the absence of direct evidence challenges our current models and forces scientists to consider alternative explanations for the formation of the early universe. This paradox between the theoretical elegance of dark stars and the elusive nature of their evidence drives much of the excitement in the field of cosmology today. What compounds this mystery further is the question of why dark stars, if they existed, seem to have disappeared from the universe as we know it. Theories suggest that dark stars may have collapsed into black holes, or that their energy source, dark matter annihilation, may have become inefficient as the universe cooled and expanded. However, the rapid disappearance of these stars raises important questions about the evolution of the universe and the mechanisms that govern the formation and destruction of cosmic objects. For now, the search for dark stars continues, propelled by the promise of future technological advancements and new observational methods. The echoes of these ancient stars may be hidden in the cosmic background radiation, faintly reverberating through the CMB, or they may have left traces in the ripples of space-time itself, carried to us by gravitational waves. As scientists continue to develop new tools and techniques to explore the universe, the mystery of dark stars may one day be solved, providing an essential piece of the puzzle that defines the earliest moments of the cosmos. Until that day comes, the search for dark stars remains a compelling and unyielding pursuit, driving us to look deeper into the void and uncover the secrets of the universe's beginning. Whether through the faintest signals in the CMB or the subtle tremors of gravitational waves, the echoes of dark stars continue to call out, urging us to listen more carefully and look more closely at the mysteries of the cosmos. The legacy of dark stars is one that, although largely theoretical, holds the potential to change the way we understand the formation and evolution of the universe. These enigmatic cosmic entities, powered not by fusion, but by the annihilation of dark matter, could have played a pivotal role in shaping the structures and dynamics that define our universe today. From the birth of modern stars to the formation of black holes, dark stars are hypothesized to have seeded the universe in ways that have left their mark on the cosmic landscape. Their theoretical impact stretches far beyond mere existence, influencing the cosmic structure that we observe around us. Galaxies, clusters, and even the formation of the most mysterious and extreme objects in the universe, black holes. In many ways, dark stars are believed to be the progenitors of the first massive objects in the universe. These hypothetical behemoths, whose mass could range from hundreds to thousands of solar masses, would have formed during the cosmic dark ages, long before the first stars ignited into visible light. Powered by the annihilation of dark matter, dark stars would have been the first significant sources of energy in the universe, potentially setting the stage for the first galaxies and the eventual formation of stars. Their gravitational influence would have had a profound effect on the surrounding hydrogen and plasma, initiating processes that led to the collapse of matter into denser regions, thus creating the seeds for the birth of galaxies and stars. These dark stars would have been vastly different from the stars we observe today, not just in their energy production, but in their entire physical makeup. Their energy source, the annihilation of dark matter, would have been fundamentally distinct from the nuclear fusion that powers modern stars. Yet, despite this, dark stars would have exerted a strong gravitational pull on their surroundings, acting as the catalysts for the creation of stars and other massive objects. The immense gravity of these dark stars would have compressed the surrounding gas, leading to the formation of early galaxies. These galaxies, which would eventually evolve into the structures we see in the universe today, would have been nurtured by the dark stars in ways we are only beginning to understand. Furthermore, dark stars may have laid the groundwork for the formation of black holes. As these massive objects began to burn through their dark matter fuel, they would have eventually reached a tipping point where their internal pressure could no longer support their immense weight. At this critical moment, dark stars may have collapsed into black holes, one of the most mysterious and intriguing phenomena in the universe. The creation of black holes from the remnants of dark stars would have had a far-reaching impact on the evolution of the cosmos. These early black holes could have become the seeds for the supermassive black holes found at the centers of many galaxies, including our own Milky Way. Over time, these supermassive black holes would grow, pulling in surrounding matter and shaping the formation of galaxies, stars, and even the large-scale structure of the universe. But the influence of dark stars does not end with the creation of galaxies and black holes. Their legacy is also woven into the very fabric of the universe, influencing the distribution of matter and energy that governs cosmic evolution. The energy released by dark stars, though not in the form of light, would have contributed to the overall dynamics of the early universe. This energy could have accelerated the expansion of the universe and affected the formation of the first atoms. Dark stars may have played a significant role in the reionization of the universe, the process by which the first light sources broke the primordial fog of hydrogen gas that shrouded the universe in its earliest moments. By providing the energy necessary to ionize hydrogen atoms, dark stars could have helped transition the universe from the opaque, plasma-filled state of the Dark Ages to the transparent, starlit universe that would later allow for the formation of the first galaxies and stars. In this way, dark stars can be seen as the architects of the universe's early development. They were the catalysts for the formation of the first structures in the cosmos, their gravitational influence shaping the early universe and seeding it with the building blocks necessary for the creation of galaxies, stars, and black holes. Without these early, dark beacons of energy, the universe as we know it today might have looked vastly different, with the evolution of cosmic structures proceeding along an entirely different path. Beyond their scientific impact, the legacy of dark stars also raises profound philosophical questions about our cosmic origins. If dark stars were indeed the first objects to light the universe, their existence invites us to reconsider what it means to begin. The universe's story is typically framed in terms of the Big Bang and the subsequent emergence of stars and galaxies, but dark stars challenge this narrative. They represent a stage before the universe was truly lit, a time when light itself had not yet been born. What does it mean to come before light? To exist in the universe without the brightness that we associate with life and energy? These questions resonate not just with cosmologists, but with philosophers and thinkers who are concerned with the deeper meaning of existence. The birth of dark stars represents a moment before the creation of visible light, when the universe was still in a state of primordial darkness, a time that by all accounts remains largely invisible to us today. Perhaps it is this very mystery that makes dark stars so captivating. They represent the unknown, the unseen forces that shaped the early universe in ways that we are only beginning to understand. By studying their hypothetical existence, we are not just probing the origins of stars and galaxies, but questioning the very nature of the cosmos itself. Were dark stars the true origin of light, or did they merely serve as a bridge to something greater? How much of the universe's story remains hidden in the shadows, waiting to be uncovered? In the grand scheme of things, the role of dark stars in the formation of galaxies, stars, and black holes may seem small compared to the vastness of the universe. Yet their legacy speaks to the complexity and mystery of cosmic evolution. They are the precursors, the unseen catalysts that set in motion the intricate dance of matter and energy that would lead to the creation of the universe as we know it today. By unraveling the secrets of dark stars, we are not just peering into the past, but also gaining insight into the very structure and nature of the universe itself. The legacy of dark stars, then, is not just about the impact they may have had on the formation of cosmic structures. It is about the way in which they challenge our understanding of the universe's origins. As we continue to probe the depths of space, searching for evidence of these hypothetical objects, we are also forced to confront fundamental questions about the nature of light, energy, and existence itself. In doing so, we are reminded that the universe, though vast and awe-inspiring, is still full of secrets waiting to be uncovered. The dark stars of the early universe, whether real or speculative, will continue to shine brightly in our minds, guiding our search for answers to some of the most profound questions in science and philosophy alike. As we stand at the crossroads of discovery, the legacy of dark stars remains an enigmatic chapter in the story of the cosmos, one that beckons us to explore further, think more deeply, and look ever more closely at the shadows that stretch out across the void. The more we learn about the early universe, the more we realize that the darkness before light holds as many answers as the stars themselves, and in that darkness, we may yet find the origins of everything we know. As humanity stands at the precipice of our understanding, we are constantly reminded of how much of the universe remains out of reach. Even with all the technological marvels we've developed, the most advanced telescopes, the most sophisticated theoretical frameworks, vast swathes of cosmic history remain hidden from our eyes. The early universe, the moment before the first stars ignited, the time before light touched the universe and brought it into view, is still shrouded in mystery. The space between the Big Bang and the first stars, the cosmic dark ages, is a realm we have only begun to explore, and even then, it remains largely beyond our comprehension. Our journey of cosmic exploration has already revealed so much about the universe, from the formation of galaxies to the dance of stars and the peculiarities of black holes. But even with all of our achievements, the quest to understand the dawn of the cosmos, before the first stars lit up the sky, is still in its infancy. The birth of light and the forces that governed the early universe before that light existed are still largely theoretical. Dark stars, dark matter, quantum fluctuations, these are all pieces of the cosmic puzzle that could hold the key to understanding the most elusive chapters in the history of the cosmos. And yet, for all our advancements, we still find ourselves grappling with the enormity of what remains unknown. Theoretical physicists and astronomers have been tirelessly searching for clues, and while we've made tremendous strides with modern tools like the James Webb Space Telescope, there is still an overwhelming sense that much more lies beyond the limits of our current understanding. Even as we develop more powerful technology and refine our models of the universe, we are confronted by questions that seem to defy our best efforts to answer them. In a sense, the more we learn about the universe, the more we realize how little we truly know. The mysteries surrounding the early universe are tantalizing and frustrating in equal measure. The cosmic dark ages were a time when the universe was shrouded in an eerie darkness, with no stars or light to illuminate the vast emptiness of space. During this period, the universe was made up of an almost incomprehensible soup of plasma, hydrogen, and unobservable forces that were too chaotic for us to fully grasp. Yet, within this cosmic void, the seeds of creation were being sown, with the formation of the first galaxies, stars, and eventually the complex systems of planets and life that we know today. But before those first stars could shine, there was a time when the universe was a place of extremes, where dark matter, quantum fluctuations, and altered gravity set the stage for the birth of everything. For years, the idea of dark stars, enormous exotic objects powered by the annihilation of dark matter, has been the subject of intense speculation. These objects, which have never been directly observed, are believed to have played a critical role in the formation of the universe as we know it. Theoretically, dark stars could have formed in the cosmic dark ages, before the first true stars ignited, and their presence would have dramatically altered the evolution of the universe. These early dark stars would have been powered by a source far more mysterious and far more powerful than ordinary nuclear fusion. Their energy would have come from dark matter, the unseen substance that makes up much of the mass of the universe but cannot be directly observed. The idea of dark stars challenges our understanding of physics and the forces that govern the universe. Unlike stars today, which are fueled by nuclear fusion, dark stars would have been powered by an entirely different energy source, one that we do not yet fully understand. Their existence would mark a profound departure from our traditional understanding of how stars form and function. And yet, these dark stars may have been the very building blocks that led to the creation of the first galaxies, stars, and black holes. The implications of this are staggering, as it suggests that dark matter, which has remained elusive for so long, may have played a far more active role in the evolution of the cosmos than we ever imagined. But even as we theorize about dark stars and the forces that shaped the early universe, we are confronted by a deeper mystery, the question of why these objects may have disappeared. If dark stars existed and played such an important role in the formation of the universe, why have we not detected them? Where did they go? What happened to them after they served as the first beacons of light in a dark and mysterious universe? These questions continue to haunt scientists as they search for traces of dark stars in the remnants of the early universe, hidden in the cosmic microwave background, and the faint whispers of gravitational waves that echo across the cosmos. As we delve deeper into the mysteries of the early universe, we are confronted by the limitations of our understanding. The speculative physics that underpins these theories, quantum fluctuations, altered gravity, dark matter's influence on the cosmos, are concepts that challenge the very foundations of modern physics. These early conditions, with their bizarre and seemingly impossible laws, are a testament to how much we still have to learn about the universe. They suggest that the universe's birth was not a straightforward process, but rather one shaped by forces that we are only beginning to comprehend. This speaks to a deeper, more fundamental truth about the nature of the universe, that even the laws of physics, as we know them, may not be enough to fully explain its origin. The search for dark stars and the secrets of the early universe is a journey into the unknown, one that will require us to stretch the boundaries of our understanding. It is a journey that demands boldness, imagination, and a willingness to embrace the mysteries that lie beyond the light. And while we may never fully unravel all of the universe's secrets, The pursuit of these answers will continue to shape our understanding of who we are and where we come from. The mysteries of the early universe and the dark stars that may have illuminated it will remain a beacon for future generations of scientists, philosophers, and dreamers. As we continue to explore the depths of the cosmos, we are reminded that there is still so much more to discover. The universe is vast, and its mysteries are infinite. But with each new discovery, we come one step closer to understanding the origins of everything we know. The cosmos calls to us to explore, to question, and to seek. And in the pursuit of that knowledge, we will continue to push the limits of human understanding, reaching ever further into the unknown. Beyond the light, in the darkness that came before, lies the key to the universe's most profound secrets. And as we continue to explore this great unknown, we will ultimately come closer to answering the age-old question of where we come from and what lies beyond the stars. As we stand at the precipice of cosmic discovery, the enigmatic era before light, before the first stars blazed to life, remains a vast, shadowed frontier. The story of the dark stars and the speculative physics surrounding them is more than just a quest to understand the origins of the universe. It is a journey that forces us to confront the deepest mysteries of existence itself. From the birth of the universe in the aftermath of the Big Bang, through the epoch of darkness, when hydrogen, plasma, and the unseen forces of dark matter reigned supreme, we have uncovered not only a history of cosmic birth and evolution, but also an era where the very laws of physics were fluid, unsettled, and unknown. The Age of Darkness, a time when quantum fluctuations and altered gravity dominated, challenges the very bedrock of modern scientific understanding. The universe, in its infant state, existed in a way that defied our traditional models. With no stars, no light, and only the hum of invisible forces shaping space and time, this was a realm where ordinary matter and dark matter intertwined in complex and profound ways. The influence of these dark forces created conditions unlike any we could replicate in a laboratory today. And yet, these forces laid the groundwork for everything that would follow. The creation of the first galaxies, the birth of stars, and the eventual formation of the black holes that would come to rule the cosmos. In the midst of this cosmic void, dark stars emerged, hypothetical objects that could have been the very first sources of light, powered not by nuclear fusion, but by the annihilation of dark matter. These stars are thought to have illuminated the cosmos in ways that still defy our comprehension. Their mysterious nature makes them one of the most exciting and speculative aspects of early cosmology. Were they real? Did they help shape the first galaxies? Could they have seeded the formation of modern stars and even the supermassive black holes at the centers of galaxies? These questions, still unanswered, beckon us toward further exploration, toward unraveling the secrets of the cosmos that remain hidden in the fabric of the universe itself. The notion of forbidden physics plays a pivotal role in our understanding of this epoch. The quantum fluctuations, the altered gravitational laws, and the unconventional forces that govern the universe's earliest moments force us to expand our imagination beyond the limitations of current physics. These concepts, such as the influence of dark matter on the structure of the early universe and the peculiar behaviors of gravity in such a young cosmos, highlight just how much remains to be discovered. Modern physics, though powerful, cannot fully explain the complexities of the first universe. There are gaps, paradoxes, and unanswered questions that we are only beginning to approach with new instruments and a growing understanding of the cosmos. The dark stars, in all their speculative glory, serve as both a symbol of the unknown and a tangible connection to the early universe. Their hypothetical existence linked with dark matter and speculative forces, offers a glimpse into the machinery that could have shaped our reality. But, as tantalizing as these objects are, their sudden disappearance raises even more questions. Why did they vanish so abruptly? What cosmic forces could have driven their extinction? And perhaps most importantly, how did these events influence the evolution of the universe as we know it? As we look to modern experiments and ongoing cosmological research, we are reminded of the delicate balance between theory and observation. The evidence for dark stars remains elusive, and yet the search continues, fueled by advancements in technology and a relentless pursuit of understanding. The cosmic microwave background, gravitational waves, and other experimental data hold clues that may eventually answer some of these profound questions. But the path forward is still shrouded in uncertainty, as we wrestle with the limits of our knowledge and the possibility that we may never fully grasp the nature of the earliest universe. The legacy of dark stars, however, endures. They are not merely speculative objects of scientific curiosity. They are symbols of our unyielding desire to understand the origins of everything. They offer a pathway to understanding how the universe's first galaxies were seeded, and how the birth of stars, black holes, and galaxies could have been influenced by forces we are still struggling to comprehend. In a very real sense, the study of dark stars is not just about looking back at the distant past, but about understanding the very nature of cosmic evolution and the fundamental forces that have shaped every corner of our universe. Ultimately, the story of dark stars and the speculative physics of the first universe invites us to confront one of the most profound questions humanity has ever asked. What is the origin of everything? From the swirling darkness of the early universe to the brilliant stars that now light our sky, each discovery adds a new piece to this cosmic puzzle. And yet, despite our progress, we remain confronted by a fundamental truth. There is still so much we do not know. In the end, the exploration of dark stars and the forbidden physics that shaped the early universe reminds us of the awe-inspiring mystery of the cosmos. It beckons us to look deeper into the vastness of space and time, to question everything we think we know, and to embrace the boundless unknown. The universe is still full of secrets, some we have uncovered, and others that lie just beyond our reach, waiting to be discovered. As we continue to push the boundaries of science and technology, we are reminded that the journey to understand the universe is a never-ending one. The dark stars may have faded into obscurity, but their legacy lives on, inspiring future generations to continue searching for answers to the most fundamental questions about the nature of existence itself. And perhaps, in time, we will unlock the final secrets of the cosmos, uncovering the true story of how light first touched the darkness of the universe.